Thermodynamics deals with the transfer of heat. Alternative variables such as pressure and temperature are generally used to describe thermodynamic systems as a whole. Thermodynamic system states and processes. Systems refer to definite quantity of matter enclosed by boundaries or surfaces either real or imaginary. Thermal isolated system. When heat transfers into or out of a system, it is impossible. However, work may be done on a thermally isolated system, thus energy transfer to it. Heat reservoir, a large separate system assumed to have unlimited heat capacity. Any amount of heat can be added or taken away without changing the temperature. The first law of thermodynamics describes how work and heat are related to a system's internal energy. Delta U, change in internal energy of a system to do work, W, done by that system, and heat, energy transferred, Q, to or from that system. And the formula is Q equals delta U plus W. For gas, the formula is W equals P delta V. The thermodynamic process for an ideal gas, isothermal process, is a constant temperature process. W isothermal equals nRT-IN parenthesis V2 over V1. Isobaramic process, a constant pressure process. W isobar equals P parenthesis V2 minus V1 parenthesis equals P delta V. Isometric process, a constant volume process. Q equals delta U plus W, which equals delta U plus 0, which equals delta U. Adiabatic process. No heat is transferred into or out of the system, and that formula is delta U equals negative W. The second law of thermodynamics and entropy. The second law of thermodynamics states that certain processes do not take place or have never been observed to take place, even though they may be consistent with the first law. In a thermal cycle, heat energy cannot be completely transformed into mechanical work. It is impossible to construct an operational perpetual motion machine. A measure of a system's ability to do useful work. A system loses the ability to do work, its entropy increases. Determines the direction of time. It is the time's arrow that points out the forward flow of events, distinguishing past events from the future ones. Entropy is a measure of disorder. A system naturally moves toward greater disorder or disarray. The more order there is, the lower of the system's entropy. The change in the system's entropy, delta S, when an amount of heat Q is added or removed by a reversible process at a constant temperature is delta S equals Q over T. The SI unit is joule per Kelvin, J over K. Heat engines and thermal pumps. A heat engine is any device that converts energy into work. A thermal cycle is a series of processes that brings the system back to its original condition. Thermal efficiency, an important parameter used to rate heat engines. The formula is backwards 3 equals net work over heat in equals W net over Q in. The thermal pump, a generic term for any device including refrigerators, air conditioners, and heat pumps that transfers heat energy from a low temperature reservoir to a high temperature. Cooling appliances are defined as coefficients of performance, COP. COP REF equals QC over WIN equals QC over QH minus QC. The Carnot cycle and the ideal heat engines. The ideal Carnot cycle consists of two isotherms and two adiabates and is conveniently repressed on a TS diagram where it forms a rectangle. Backwards 3C equals 1 minus TC over TH. The third law of thermodynamics. It is simply impossible to reach absolute zero in an infinite number of thermal processes. The following problems that will be demonstrated are not challenging at all, as I take you step by step to show you how to solve these problems using the formulas that you learned throughout Chapter 12. The first law of thermodynamics, where delta V equals Q minus W, Q equals heat, and W equals work. Right here in the problem where positive Q goes into the gas and work is done to the right, W equals 200J and K equals 500J. So we plug it in to figure out what delta V is, because this is going to be your change in total energy. So delta V equals Q minus W. You plug in 500J because that's what K equals, and then you subtract 200J from the 500 because that's what work is. So your total change in energy will equal 300J. So heat is a form of energy. So for our problems like KE and KE blocks colliding or PE falling down, you would see that the Q has an effect on both types of problems. For example, the Q enters in from the top where it's positive and it goes to the bottom where it becomes negative. So that type would go into our PE problem. The measure of a relative or hot and cold. So that's what temperature is. That's the definition. The measure of relative of hot and cold. So it'll tell you if it's either hot or if it's cold. And for right here, when they collide, it becomes thermal equilibrium because they want to become the same equal temperature. Right here will be hot and right here will be cold. This temperature will go to this temperature to make this one hot and then this one cold. So they'll eventually end up balancing to an equal temperature where they'll both be satisfied. This is the problem that I'll be working on from collegeboard.com. It is an AP problem from 2009. So for the College Board problem, we're required to solve different things to solve for the main problem for the equation. So for part A, P equals P ATM plus mg over A. And basically that's just asking for the formula that we're going to use, and that's one of them. The cylinder is a vacuum, and so you need to state that. And then for part B is where I actually start doing work. So 1 RP equals backwards 3, 1 over RI. Then you kind of do your work, and then you get 1 over REQ equals 1 over RO plus 1 over RO plus 1 over RO equals 3 over RO. REQ equals 3 over RO over 3. And so that's our answer right here. That's it. And then for C, part C. So right here is another thing that we have to solve for. We have to solve for U. And this is the formula that we're going to use. So you use delta U equals PCIR T. PCIR equals E, or backwards 3, squared over REQ. So this is a formula that we plug in. So delta U equals parentheses backwards 3 squared over RO over 3 parentheses T. So our answer would be delta U equals 3 backwards 3 squared T over RO. So that would be our answer for C. And now for D. Okay, so basically we're going to use the first law of thermodynamics, which is delta U equals Q plus W. We know that Q equals 0. So for right here, the net loss of energy in the gas, and thus the internal energy, decreases. Because since temperature is decreasing, so is energy, because energy relies on heat. So since Q equals 0, energy will go down. So your answer for D would be decreases. And then right here for our chart, V always goes right here on the bottom, and then P goes right here. So it's kind of like your XY chart, but V is replaced. X is replaced by V, and P is replaced by Y. So energy is proportional to the temperature, and the temperature must also decrease. Well, that was for D. Sorry, my bad. Basically right here, that since for the 3 answers we plug in, we kind of get a triangle as we graph it. Right here's our O, and then we just kind of like form a triangle. It goes cricket.